And very quickly, so that for those of you who aren't here, you can do a bit of catch up with this here. We're talking about what you saw last Thursday, where we had the sodium light, which gives you these concentric rings. The idea is we're trying to get an equation that relates the fringe spacing with the thickness of whatever's holding up at a wedge fringe there. If we can do that, then we can do something similar for Newton's rings. Introduced the idea of phase change last week, where you had the slinkies reflecting backwards and forwards. If you go off a more dense background, then you get a phase change of pi, or in other words, it's sort of half a wavelength extra. Less dense, there's no phase change, and in both cases, there's some wave energy transmitted. And that summary you'll be able to download there. So, talked about what happens when you get two reflections, one off the inside of the top microscope slide, and the second off the bottom surface there. That has zero phase change, that has a pi phase change. The only thing that's going to introduce any other change in the wavelength is the distance between there and there. And then if it's angled, you've got two of those double reflections there and there. And if these two arrive out in phase, then you'll get obviously constructive interference. And it was a case of how much further did you have to go along to get the second double reflection to also give you constructive interference. And that's the fringe spacing delta x. And this extra distance, because it's a there and back distance, we worked out was half a wavelength of the light that you're using. So the angle there, theta, you could get as being in a triangle here, that you had theta there, is lambda over 2, and delta x, and use tan theta is lambda over 2 divided by the adjacent, so 2 delta x there. And then on the bigger scale, if we then thought, right, what's happening overall, you have the theta for the whole thing, and if we draw a second triangle where we've got theta for the whole length of the slide, so that's the length of the slide, and that's the distance which is being held up by a bit of gold film or a hair. In that case, for the same similar triangle, the same angle, tan theta is now that small distance divided by the length. And if we equate those two equations for tan theta, we've got the d over L equals lambda over 2 delta x. And you can cross multiply that to give you, I'm just going straight back up to the top here, delta x equals lambda L over 2d. That's the equation that the SQA will give you. Okay, so that's it there. So lambda L over 2d is the equation that is on your formula sheets. And what that's giving you is the fringe spacing, delta x, in terms of the whole length of the slide there, the wavelength of light that you're using, and the thickness d in there. All of those would have to be in meters for it to work best. Okay, so that was just from what we did yesterday, for those of you who were off.